friends, good morning. Welcome to my amazing sa pyara sa channel Physics Universe. I hope you are all fine at your home and we are enjoying this online lectures. So today our topic is the dipole in a uniform magnetic field. So this topic is when we put any magnet or magnetic needle inside a uniform magnetic field. We know about uniform magnetic field that magnetic field lines are always parallel to each other, so that is uniform magnetic field. So when we put this type of bar magnet inside uniform magnetic field, the force is exerted on that particular bar magnet due to external field. So due to that force, on north pole the force is in the direction of magnetic field, on south pole the force is opposite to the magnetic field. So there will be torque because of couple forces, because of opposite forces, and they help each other and forms one torque. So tau is equal to vector m cross vector b. Now what is m? M is magnetic dipole moment. Clear? Okay, so there will be cos cross. Cross means sine function. So sine theta, theta is the angle between magnetic moment and magnetic field. Clear? Okay, now we have torque formula again. What is torque formula? That is I inertia into alpha. So I upon alpha, I into alpha is torque, another formula. So here tau is equal to mb sin theta is equal to I alpha. So if in this particular example, if our bar magnet is in equilibrium, then there will be restoring force applied by that bar magnet. So that's why I have to kept a negative sign in this equation, and I alpha is equal to that minus mb sin theta. Now alpha is nothing but d2 theta upon dt2, means double derivation of our uh, double derivation of our angular displacement. Clear? Okay, now again we are moving further. That sine theta in this equation, particular sine theta is very small. If it is very small, then sine theta is theta, so now we put it here mb theta. Clear? Now just subject d2 theta upon dt2. By subjecting it, we get this formula minus mb upon I into theta. Okay, so minus mb upon I into theta. So this left hand side is nothing but it is omega square into theta. So this equation is omega square into theta. If we put it in this equation, then theta will be cancelled out and we get this omega square is equal to mb upon I. Simple as that. By that mb upon I, if we put omega's formula, what is omega's formula again? It is 2 pi upon t. T is our periodic time. So by putting it in this equation and t subject, we get 2 pi under root I upon mb, this formula. And from that formula, if I subject magnetic field B, then I get B's formula in the form of periodic time and moment of inertia. Here, so that's how we get, whenever we put bar magnet inside uniform magnetic field, this is the magnetic field formula. Okay, now if we, by putting bar magnet inside magnetic field formula, we find we get also potential energy there, because there is the restoring force. Because of restoring force, we get potential energy as well. So potential energy is nothing but integration of torque into displacement. It is like work formula, work is equal to force into displacement, but here potential energy. So what is torque formula? mb sin theta. Simple. Now sine theta's differentiation is minus cos theta, so our potential energy formula will be minus mb cos theta. Cos is a function of scalar product, so I have to write minus vector m dot vector b. क्लियर? अब यहाँ पर डिफरेंट केसेस के अकॉर्डिंग पोटेंशियल एनर्जी चेंज होगी. सपोज हियर माय थीटा विल बी 0, देन cos 0 is 1, so I get very minimum potential energy there. If my theta will be 90, cos 90 will be 1, sorry, cos 90 will be 0, then I get potential energy will be 0. If my magnetic moment and magnetic field both are in opposite direction, then cos 180 will be minus 1, so minus minus plus, so at that particular case we get maximum potential energy. Clear? So this is how potential energy will be changing with changing its angles. So that's all for today, guys. Thank you so much for listening my video lectures till the end. That means a lot to me. Thank you very much.